The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. This is Jennifer Beliveau, sales representative from Applied Math Modeling, and today's moderator. Thanks for joining us online today. We're excited to share with you another great case study using our new CoolSim version 4, improving the energy efficiency in the data center using CoolSim 4. With me on the line today is Paul Bemis, Applied Math Modeling's President and CEO, and Liz Marshall, our Director of Technical Support and Services. Before we get started with the presentation today, we'd like to inform you that we're going to have a question and answer session at the end of today's presentation, and you can enter your questions in the question panel that is located on the right-hand side of your screen. If you do have some technical difficulties, please click on the raise hand icon and we'll respond to you through the chat window. So without further ado, let's get started. Paul?
Thanks, Jennifer, and welcome everyone to the program. Hello, Liz, and welcome to the program as well, to you.
Thank you.
Today we're going to talk about energy efficiency again using CoolSim version 4, which is the new release that we have announced just a couple of weeks ago. And in CoolSim 4 are some neat new features that we think you'll find helpful with respect to overall analysis of data center energy. So before we get started, I'm going to review, for purposes of education, just some factors or some metrics we're going to be using in the webinar. Now, for some of you who have attended others of these webinars that we've done, this is going to be review, but I think it's important to set the foundation consistent for everyone with respect to acronyms and three-letter acronyms and definitions before we get started. So the first one we'll do is PUE. PUE is total facility energy divided by IT energy. And it's really a measure of how effectively the data center is delivering cooling to the IT equipment itself. The total facility power is made up of the IT equipment plus everything else that takes energy, such things as batteries and PDUs and transformers, and of course the cooling system. But when you look at that big long list of things, you find that the dominant characteristics are really the cooling system. The cooling system itself makes up 75% of the non-IT load in the room. So things like UPSs, inefficiencies in UPSs and PDUs are all second order. The primary element, the primary thing, is the crack and the chiller, the heat pump. It's getting the heat out of the room that is the dominant characteristic with respect to energy. So PUE is really, from a dominant parameter point of view, cooling energy plus IT energy divided by IT energy. If you look at the metrics and which ones are dominant, it's really cooling energy. And focusing on cooling energy, therefore, and cooling efficiency provides the biggest payback, the biggest return on investment. And understanding how that system works is key from both an operational point of view and, of course, a data center design point of view. So let's go forward a little bit here and talk about the cooling system energy efficiency just a little bit. Cooling systems are effectively heat pumps. They're taking heat from the data center and pumping it outside using mechanical shaft power. That's how they do it. It's an electric motor. It drives a mechanical device, and it takes heat out of the room through a process of pumping, a heat pump. They all work the same way, whether it's a refrigerator in your home, the air conditioner in your home, or the data center. They all work the same way. And there is a relationship here that they use called coefficient of performance. The coefficient of performance is a ratio of the thermal load in the room, including the fans, which produce heat, divided by the energy required to cool the data center. It's this ratio that we're interested in. Now, the heat pump manufacturer or the crack manufacturer will also talk to you about COP. Theirs tend to be higher because they're not talking about the COP of the room. They're talking about it of their machine in an ideal environment. Furthermore, they use something called EER, which is actually kilowatts per ton ratio. Liz and I tend to use COP because it's dimensionless, it's kilowatts per kilowatt, and it's just simply a ratio of the amount of heat rejected compared to the amount of work required using the same units to get that heat out of the room. So we're going to be talking here about COP of the room itself, and this is a fairly easy thing for you to get your hands on, whether you're designing a data center or whether you're operating one. In the operating case, it's actually fairly straightforward to get your hands around these parameters. And we'll talk about how to do that. So COP is one that we're going to talk about. It ends up that COP, because it really, if you look at the dominant parameters in the PUE metric, you find that COP is the dominant one, and that therefore PUE is really the inverse of COP plus 1. The way to think about this is that a good COP would be about 4, which means that it only takes 1 kilowatt to reject 4 kilowatts. It only takes 1 kilowatt of electricity to pump 4 kilowatts of heat out of the room. That would be a good COP. And therefore, if you had 1/4 plus 1/4 would be that ratio, plus 1 is 1.25, and that's good PUE. So it's a fairly easy way to calculate PUE and to think about it. And the way to really get your hands around it is to measure the amount of energy that's being consumed by your cooling system and compare it to the energy being consumed by your IT equipment. Just compare them. The energy being consumed by your IT equipment is easy to see because you've got a backup system, a diesel generator or something, batteries or something standing by, and you often, most likely, have a meter on that looking at the amount of energy being consumed, because that's, of course, what you need the remote system to be able to handle, the generator. The cooling system is fairly easy to do as well because it's generally on a separate circuit itself, and you can at least put a current measurement device over those leads or the power and measure it. An electrician can measure it. An electrician can come in, clamp the current coming into the cooling system, particularly for DX systems, and give you at least the current coming into the environment. If you can get the current, the amps, coming into each of those cooling systems, with a hand calculation you can determine at least instantaneous kilowatts, and that gives you some kind of baseline. And that's generally what we use. That's what we run on, is some kind of number like that. Chillers are a little more difficult, not because you can't measure them the same way, but because chillers often are being shared by other rooms, and so you have to try to proportion the amount of energy being consumed by your room compared to others based on size and load. But nonetheless, the basic idea is the same. Measure the amount of energy being compared by the cooling system, or being consumed by the cooling system, and then compare it to the energy being delivered to the IT environment. So if we take a look at a simple cooling system, this is one that's a fairly good illustration that I looked at. They operate on the idea of phase change. And so this is a simple little circuit here that shows how these work. Generally, you have a medium that changes phase in here, and when you compress it with mechanical shaft power, the medium gets hot, and then you dump it to the atmosphere through some kind of condenser. And then because you've dumped the heat, you go through, it's under high pressure on this side because you've pumped it up, and as it goes through an expansion valve, the temperature drops and it gets cold. You go through an evaporator where it gets warmed up by the environment. The heat transfer is from cold to warm here. Remember, heat temperature always travels downhill. So the evaporator, the medium, gets warmer down in this section, and then comes back up, gets compressed again, and back up and around. If you take a look at a diagram here, this is a temperature enthalpy diagram, or entropy diagram. You see here that we go from point 1 to point 2. This is where the work goes in. The shaft power goes in here, and we're driving up the pressure and therefore temperature, and then the heat begins to dissipate out. Temperature drops to a certain point, and then the medium changes phase, and we go over here to a saturation point where it can no longer absorb any more heat. In an ideal situation, we would then drop straight down with no entropy to what's 4' here. Of course, the world is not ideal, so it does actually come down to here. And then we go through, we absorb heat and so forth. The energy required to run this process is contained in the area inside this curve. That's the work. So to reduce the work, what we want to do is move this line, the 1,4 line, up closer to the 2,3 line. Reduce the amount of work by reducing the T, the delta T, that needs to be attained, which is directly related to pressure P because of the ideal gas law. So the less pressure you have to create by the compressor to get to that higher temperature, the less work you have to put in, the better the COP. They call that delta P, that pressure, lift. So reducing the compressor lift reduces the energy consumption. And there's a couple of ways to do it. One of them is drop the temperature of the condenser down. The water entering the chiller, if you can get it down, that'll do it. Or if you can get number 4 up, which is supply air temperature, and we'll talk about both of those. So here's a chart. This is from an ASHRAE, the standard ASHRAE manual on data center efficiency, that shows that by increasing the cold air supply temperature, the COP improves. And that was my point I just made in the chart, that by driving up the supply air temperature, you get an improvement in the overall efficiency of the system, meaning the COP goes up, and it goes up at a rate of approximately 2% per degree F. It's actually 3.5% for every 1.8 F, so it rounds out to about 2% energy efficiency improvement by increasing the cold air supply temperature. So you want in your data center to try to drive the supply air temp up as high as you possibly can to save energy. That's what that's telling you. The other chart I have here is the condenser temperature itself. If you can drive down, if we move along this axis right here, we drive down condenser water temperature, which means the water entering the chiller is colder, therefore that top line in my diagram is moving down, the COP goes up as well. Now you'll notice the COP here, these can get quite high. You see what was 13.7 here, but look at the delta T. My chilled water temperature is 55 degrees, and my entering water temperature 60. I'm only moving this thing 5 degrees. So if you're moving it only 5 degrees, then your COP is quite good. And again, you come up with a similar ratio. As you decrease the condenser temperature, you'll improve the chiller efficiency by about 2% as well. Now these are chiller numbers. DX units, direct expansion units that work in the data center follow the same pattern because they have the same exact cycle. The only difference is in a DX unit, the evaporator is directly exposed to the air, where in a chiller, you've got the evaporation loop removed one level through another water loop. There's a water loop between the evaporator and the room itself. Otherwise, they are the same, and there's no reason why a DX unit can't be as efficient as a chilled water system when they're set up correctly. At least that's what most people argue. So, okay, so techniques for improving. Again, what we try to do is get the temperature across the heat exchanger as big as we can get it. Maximize the temperature difference across the heat exchanger. And that's simply because that's the potential for heat transfer is delta T. It doesn't work without a good, solid difference between the two temps. So that also increases the hot air temperature in a data center, which allows you to run with lower exiting condenser temperature or entering chilled water temperature. And you need to increase the cold air supplies as high as possible. Now here's the tricky part. You can't increase them too high without typically running into some trouble in the data center, and that's where CFD comes in. So what we do is we try to drive up supply air temp as high as we possibly can without causing problems in the room with respect to the servers. And we use CFD to model the behavior as we increase supply air temperature in the data center. And it's all governed by the same equation. They use a fan coil system on both sides to transfer heat, and therefore the relationship is that heat transfer Q is equal to the mass flow rate times the specific heat of air times delta T. Delta T is the return supply difference. So the cooling system and the computers themselves respond to the same equation. They are exactly the same. And you see here we've got a mass flow rate number that's quite important. We'll talk a little bit more about that as we go along. But, of course, the supply and return deltas are important as well. If mass flow rate is too high, the delta T is not so good on a cooling system. And we'll talk about that and illustrate that in a moment. So it's important to maximize the difference between the coils, between the temperature across the coils to get good heat transfer. It's also important to keep an eye on that mass flow rate, particularly in the case of the cooling systems, because if the mass flow rate gets too high, the delta T by definition will drop. So it's important to understand that relationship and how it works. So what you do to improve the efficiency of your data center is first determine the total amount of airflow required to satisfy the IT thermal load. And a general number we use is about 156 CFM per kilowatt. That's a good rule of thumb. It does assume a 20-degree delta across the servers. The number just simply falls out of that last equation I showed you, where the density of air at sea level times a 20-degree delta ends up being 156 CFM for a kilowatt of heat. It just falls right out of the equation. There's nothing magic here about that number. And then what you try to do is reduce the supply airflow to match only what's needed by those servers. In a perfect world, you'd have a cooling system lined up right in front of each one of the servers, and the flow rate from the cooling system through the server would be the same, exactly the same. Now, you can't quite do that in a data center, but you're trying to achieve the same goal. You want the supply airflow from the cooling systems to be only enough to match what is needed by the servers and no more. Because if it's greater than what's needed by the servers, it's just going to blow by the server and go back to the cooling unit, and when it goes back to the cooling unit, it's going to cool off the return air temp and reduce your efficiencies. So this maximizes the return air temps, and it saves operational costs, of course, on fan energy, which can be significant. And then what you try to do is drive up air supply temperature until your worst case condition gets close to 80, 80.6 or higher, depending how aggressive you would like to go. And you use containment to unify your rack inlet temps. Because without any air management, the rack inlet temps will vary quite a bit across the room. And you use containment to unify them and get them more even. So we have a couple more metrics we use to look at this situation. These are more popular in recent years, introduced as part of the Data Center Energy Practitioners Program. And the first one that we'll take a look at is RTI. RTI is really the ratio of what is required by the racks compared to what is being supplied by the cooling system. It's just a simple ratio. And what you see here is that if the air handler, this is either crack or cray, however you want to look at it, if the cooling air flow rate is greater than the rack flow rate, it's going to drive this number down. If these are identical, if these are even, you're going to get 100%. If you don't have enough airflow here, this number will go positive. It'll go over 100%. So you see that it's balanced at 100%. If it's greater than 100%, you've got rack recirculation because you don't have enough air to supply the racks, and it will just wrap right around and go back in. They'll be breathing their own exhaust effectively. And if it's less than 100%, it'll be going right by the rack and back to the cooling system and cooling it off. So this is the first one that we look at, RTI. What is the ratio of the airflow in the room? How much air are you supplying compared to how much you need? Fairly easy calculation to do. All of the cooling systems have specifications on what their flow rates are. Look them up, add them up, take a look at the total load in your room, multiply by 156, and compare the numbers. And that's a first approximation of where you are. The other metric we use is a little more difficult to ascertain. This one is called Rack Cooling Index. And here what we're looking at is what percentage of units, samples in the room are over temperature compared to the maximum over temperature total amount. So here we're looking at, this is really a ratio of compliance. How many over temps are there and how large are the overtemps. Now, generally, this is done using sensors, or originally the idea was to use sensors to calculate these metrics. We use CFD to calculate these metrics, so we're actually getting it a little more detailed than could be done with sensors, because we have meshing, and meshing is a grid, and the grid is on the front face, and we can sample many, many points. But we've built these metrics into CoolSim 4, so you don't have to calculate these by hand anymore. In the DCEP training, they actually gave you spreadsheet methods for calculating these. You don't need to do that anymore when you use CoolSim. It's calculated as part of the overall process. So those are the three metrics that we're going to be using: PUE, RTI, and RCI. And the data center we're going to be looking at today is a standard 4,500 square foot raised floor data center. It uses natural convective return. It's got about 70 kilowatts of IT load. They're using 4 Lieberts in it. And the process we'll use is to validate the model, perform baseline energy calculations, and then begin to modify by first going for RTI, trying to get the air in place. And then we're going to use some containment to optimize the airflow. And then we're going to be able to walk up the cold air supply temp and see how far we can get. And this particular model it's a fairly straightforward data center. This one's DX based. So our ability to move the RTI number a long distance gets constrained by the fact that they're DX units themselves. Mm-hmm. But this is a very typical data center in the sense that, and this is a real live data center, this is a colo that agreed to allow me to use their data center for analysis purposes here today. 4,500 square feet. Now, this is also very typical, is what they often do is build it for worst case analysis. Mm-hmm. These are, I believe these are 30-ton units roughly, 30-ton cracks. So they've built this thing for, and the kilowatts there is really 412. So they've built this thing for 1.6 kW of total load, or megawatts of total load, and they're running it at 70. Mm-hmm. Mm-hmm. We see this a lot, don't we?
We do, yeah. Yep. Way too much air. Way too much air, way too much cooling.
Right,
mm-hmm.
Right.
Very common.
Because what often happens, most always happens, is the design team that built the data center, that laid it out, built it for worst case conditions, right? Mm-hmm. Because of course they're building it, they want to make sure under worst case conditions that it handles the situation. And then the owner takes over and puts in, 7 racks mm-hmm. Mm-hmm. and turns all the units on.
Yeah, or they're lightly loaded. That's the
Yes.
other thing that people can't really anticipate. In reality, the actual heat loads on the servers is quite a bit less. Is often less than the nameplate ratings, and so that's why measurements are important if they can be made.
Yes, very good point. I mean, oftentimes, even in the IT world, they overspec, right? Mm-hmm. So the IT manufacturer will tell you, well, that's a 2 kW box, and you put it in and you find it's reading, 1.2 or something. So mm-hmm. everybody worst cases the situation, mm-hmm. and as a result, the optimization, the efficiency of the energy in the room is terrible because mm-hmm. it's way off its design curve. So the way that we validate models, the easiest way that I have found to do it is measure the supply air temperature coming from the cooling units and use this as a boundary condition for the crack units in the CoolSim application. That bounds the situation, it bounds the problem. So what we do is we ask the customer, or we measure what the cold air temp is. Just put mm-hmm. a probe under the floor in a raised floor case and measure what the cold air temp is. You also want to measure the return temp at that same point, because we're doing an instantaneous point here. We're looking at it at one point in time. To be honest, the supply air temp varies depending on whether the compressor is on or off. Mm-hmm. But if you take a snapshot in time and then build a model based on the snapshot and validate your data, at least you know that the physics are being captured by the model. Mm-hmm. Then we run the model. We compare the predicted crack return temperatures with the measured values. And if they compare within 10%, then the model is predicting the physics in the room fairly well. If not, then you go back and take a look at your equation and say, why not? Mm-hmm. Right? Because mm-hmm. if we have the return temp in the supply temp is fixed because we set that as a boundary condition. The mass flow rate is being defined by the crack units themselves. The heat load is the IT equipment, so that's fixed. And the density of air is going to be the same. So the only thing that can be wrong is if the return temps don't match, then your mass flow rates are off.
And that's common too for older units, because the filters get dirty, or something happens that degrades their performance. And so we've seen people doing measurements in the field tell us, we've had people tell us that in fact the rated mass flow rates are not always what they are, or the measured mass flow rates are not always what the published values are, depending on the age of the unit. So. And
what's going on under the floor. They can also be walking a fan curve too.
That's exactly right.
So if the delta P is too high, if there's too much resistance under the floor, if the subfloor is 8 inches or 6 inches, or there's 30–40% of or more of the cross-sectional area is blocked, then it's likely that the fan will not be producing what the spec is, because it's got too much pressure drop across it. So that's something to look for. So if more model validation is required, you can go to a next level. The next level is measure the airflow rates coming from the tiles or the diffusers, depending on the kind of data center, and compare those with that predicted in the model. Now, this gets a little more difficult, a little more involved in terms of time, because you have to make measurements. And measurements are, by definition, subject to error, human error. First of all, we'd recommend you use a back pressure compensated bolometer. Those can vary. If they're not back pressure compensated, we've learned that these can be off by up to 30%. And the first thing you want to do is to measure the total output of all of your outlets, diffusers, tiles, and make sure that they match what you've got in your model. And again, back to this issue of walking the fan curve, if what you measure doesn't equal what's being delivered by the spec on the fan, then there's an issue there, right, Liz? I mean, there's a reason why.
Yeah.
It's usually pressure or belt slippage or age. And if it exceeds the total in the model, then reset the cracks on the model, because I have seen them go the other way too, where they over-deliver. The specification says 10,000, they measure them, they're producing 12. So there's that case too.
Yeah.
And then check the balance in the diffusers, see how they compare to the model. So once we've checked the total flow, then we look for distribution. Is it being distributed evenly, or not necessarily evenly, but at least proportionately to what's in the model? If not, then there's a reason why. There's usually an underfloor obstruction, or one of the grills is shut, or one of the diffusers are shut, or something. So it's really a three-step process, I would say. First, look at the delta T's on the cracks and make sure they're valid. Then take a look if you want to go further. Oftentimes, delta T's on the cracks are enough, because you've captured the physics. You're just looking for rough parameters. You're trying to get your hands around the big things. But if you want to go further, then look at the measure the flow rates. And first, the totals need to match. The total being measured needs to equal the total being delivered in your model. And then look at distribution. And generally, we find these line up quite well. Now, here's, in this case that we are looking at today, there are 4 crack units. I set the supply temperatures to be 55. And this is coming right out of our summary report that's produced as a result of the output. The average return temperatures...
These were measurements from the client side, too. You
That's
might
correct.
Point that out. They look very cold, but this is where the client was
This is where the client was operating. That's exactly right. When we did this analysis, they were operating at 55. The return temperatures were predicted to be 59, 61, 58, and 59, and the measurements are shown here. So the average error here is 1%. It came in quite nicely. Now, we want to point out that this is not quite an apples-to-apples comparison, because the return temperature is not a constant either. If you look at the return temperature, there's a sensor somewhere that is measuring the temp in the real world, and it's measuring the temp at a given point on the surface area of the return plenum, usually at the top of the crack. But that's only one point. There's actually many points. Remember that temperature is not uniform across the entire return surface. of the crack unit. And as a result, they're just picking one point. In CFD, we have a mesh. A mesh is a polygonal representation that sits on top of that crack unit, and the mesh is fine enough so that we have many points on that surface. So ours is actually an average of all of the points on the surface averaged instead of just one point. So it really isn't fair, even Liz here, to say average return. Or what? No, I did say measured. I called it measured return, but this is a point, and this is really an average. They're really not apples to apples.
Right.
So 10% is reasonable, is my point here. You know, if you're within 10%, you've captured the dominant physics in the room. Now, to go further, here is from, again, our summary report. These are all printed out, and I'll show you this in our summary report. I didn't list them all because there's so many it wouldn't fit on the page, you wouldn't be able to see it. But here I've cut out the middle section. You can see I jumped from 1 to 17, but you can see what's going on here. Here's what's predicted by the model, and here's what was measured using a bolometer. First of all, the totals are very, very close. The totals are within 1%. That's the first thing you check for. And then you look for variation, and you can see the average error and variation is 6%. That's an absolute value of variation. So I'm looking at variation to either side and looking at the average of the absolute value of the variation. And I get about 6%. So I feel that model's quite representative. By the way, I don't have any underfloor obstruction at the moment in the model. And I'll show you the model here in this view. Now here what we're looking at is the model of this data center, and I want to point out a few things about this. First of all, this is a colo, and these are cages. These are mesh cages. You don't really need them from an airflow point of view because they're mostly open anyway. I put them in mostly for aesthetics so that it looked appropriate. We're using baffles here, and they're semi-transparent. But you can see from a top view, these are all sections. So a client is in here, and a client is in here, and so forth. Kind of a funny shape of a room. You know, it's not exactly the design that I would pick out, Liz, if I were to pick out a room. This one's kind of funny in the sense that, I mean, if you look at it from a top point of view, and you see that it's kind of a funny design. So
well, it's probably part of a larger building, and you know, other things are going on, and it grew into this space. And
that's right. Yeah.
I think there's a history associated with a lot of the data centers that we see.
That's right.
How they got to be where they are and the shape that they're in. And
that's
what's
exactly.
Where. Yeah.
You can't always predict or define how you
exactly based on what your starting conditions are.
Right. But you can see here that this does have a ceiling plenum. That's a good thing. So we do have air coming back to the cooling units via the ceiling plenum. That's nice. I like that. But it's basically naturally convective back. It's not being channeled in any way. There's no baffling going on. There's no containment going on. It's just coming back through the ceiling plenum. Now, let's take a look at the summary report. By the way, this is what a set of CoolSim output looks like in version 4. I'm showing you the entire set. This is exactly the way it comes back to the user. And you notice I'm showing this to you inside PowerPoint, which you can do as well as a user. The results of a CoolSim run don't live exclusively inside of CoolSim. You can export the entire set of output for any run and view it using a standard browser, put it into PowerPoint, make 3D images out of it, share it with your friends and family, put it on Facebook, you know, whatever you like. But one of the key features we've added in version 4 is the data center energy report. Now, here we're calculating the COP, PUE. We also give you DCIE, which is just the inverse of PUE, RTI, which we talked about earlier, RCI, high and low, total facility power, and annual cost. So during the setup of the CoolSim model, you have the opportunity to enter information into the model about either readings or assumptions you're making associated with this data center, such as cost of electricity, and it will calculate for you these metrics. So it's a nice way to get away from hand calculations and have it be done by the program so that you can present it like this to your boss, your friends, your customers, whoever. So the summary report contains this, and there's a few things we can note about this right away. COP, Liz, 1.59.
Pretty low, pretty low.
Awful. Yes. PUE 2.3, which means that we're spending as much electricity powering the cooling systems as we are
Yeah, and then
powering
some.
the IT equipment. And then
Yeah.
some, that's right. RTI, 18%. Just awful. Now, the reason that's true is if you take a look up here, we only have 70 kW of load. We've got some heat being transferred into the room, actually, into the room, because we're running the room at 55 degrees. So we're cooling adjacent spaces. So we've got a total heat load of 75 kW. So normally that would want a total of 10,000 CFM, at least the 70 kW would. It'd want 10,000 CFM. But we're generating 60,000 CFM. So we're off here by a factor of 6. And that's what's driving this number so low. Now, some of you will argue this is unrealistic. Liz, this is what we started with in this program. This was a real case study. This is not that unusual, as you know. We see this a lot.
We see it all the time. We see it all the time.
I think the point is no one's paying attention, I guess. You know, or maybe the fact is they're beginning to pay attention now.
Yeah, no, I think that's true. People are beginning to pay attention for sure.
So we see here that the cracks are running at 55, and the delta T's are awful. Look, we've got 5 degrees. Look, we've got 3 degrees across these two. 3 degrees of delta T. Now, what this means is the heat removal's not very much. The efficiency of this unit is lousy. The compressor's running on and off. It's cycling. It's blowing a lot of air. Terrible. Terrible waste of energy. By the way, the maintenance cost on this unit is going to be high too because it's cycling on and off. Can't figure out whether it should be on or off. It's underloaded. It's running way below its design point. They don't work well there, so maintenance is going to be high. Reliability is going to be impacted. And it's failing the ASHRAE spec with respect to cooling. It's too cold. The specification says 64.4. And we're running this thing down to 55, so we're below the spec. And that's why back in the energy report, we have it less than 0. Actually, the calculation shows it as a negative number. We decided the best thing to do here is just say, yeah, it's 0 or less.
Yeah. Forget about it.
A couple other things we've done in CoolSim 4, which are kind of nice. We still do the full range rack inlet temps, where you can see the full contours here, and you can see the contour of temperature across the range that's being seen by the model. But we've also added a couple others. One of them here I like. This is a ASHRAE recommended plot. So what we've done here, and Liz did this work, and it's very nice work, what we've done is we've said the range of acceptable behavior for these rack inlets is set by Class I standard is 64 to 80. If you're in that range, your rack inlets will be green. If you're below it, they'll be blue. If you're above it, they'll be red. So we call this the kind of the Visine test, get the red out, you know. But also the blue is too cold. So you can tell in one quick snapshot whether or not your servers are within spec. And you can see here they're not. So the combination of the summary report and this representation here I think are very nice. We also have one which is allowable. The allowable gives that range a little higher, 90 degrees, 59 to 90. And you see here that some racks are beginning to come into a range on the allowable. We can change these, make these anything at any time, but I think it's a nice way to look at a plot and see whether or not it's within range. We have a bunch more that we can look at. We have, of course, slices. This slice is actually a fairly good representation of what's going on in the room. So you see some heat being generated there, but not very much. That room is stone cold. And we also have pathline plots. And I'll show you the pathline plot from the tiles. And you can see what's going on. It's a hurricane in there. I mean, these are pathline plots that are coming up and out. And the way that this should work is that you should see no path lines in the room, that the air should come up out of the tiles and into the rack and stop. You should see no flow in the return ducts, because all we're showing here, Liz, is just supply, right?
Exactly. It's very cold air, and it's just blowing all over the place, way over and above the racks, and
right.
Just because there's way too much coming out of the supply, out of the perf tiles.
Yeah, look at it blowing by right here, and this is a good example of bypass airflow coming up. Not going in the rack at all, going right back to the crack unit. And going back cold, as you pointed out. So this is going back at a temperature that is, 60 degrees, 58, 60 degrees, which means the delta T's are very poor in the crack, and the whole thing is terrible. This is also a good illustration to show a customer, if you're a colo provider, and you show them that the room is just way too cold, because customers will often push you to run them more inefficient than you'd like, because they want to make sure their equipment is, quote, safe. We also have animation sequences here, and every time you do a CoolSim run, the same data comes back, the same set of plots, the same set of output. You do not have to push any buttons or return any dials to get this to happen. It's a fully automated scripted sequence. So here's what came out of it. This is the actual plot or the data center energy set that we were looking at. And you see here that the RTI is 18. The RCI high is certainly no racks are over temp, but we've got a problem here with low. So we're wasting energy. The estimated cost to run this data center for a year is about $150,000. Now, a couple of points here, Liz. COP is not constant. We know that. So you have to, as a design person or an analysis person, you have to pick a spot and compare to it. So we in CoolSim 4 have given you the ability to put in either COP or measured power at a point. It's only a single point. It's not a function yet. It doesn't vary over time, but it is a beginning. It is a start. And we think that makes sense. Now, over time, we'll get more granular. Maybe we will allow you to put in a function, or maybe you can couple it to a 1D code that's predicting the average COP for the year, or based on external temperature of the environment, what have you. The fact is that you can calculate an estimated annual cost based on an average COP and then look at change. I guess the point, Liz, is that change is relative, right?
Yes. Yeah.
So it doesn't necessarily matter. Just draw a line in the sand, you know. And
well, you pick a point, you make some measurements, you validate the model, and then you modify that model to see how you can improve it. And hopefully those improvements will scale with, when the fluctuations of the data center. Exactly
right. So it doesn't necessarily matter what the COP is to begin with. I mean, when I was in the Energy Practitioners course by the DOE, their methodology, Liz, was if it's a DX unit, the COP is 3. If it's a chill water unit, it's 4. Because at the end of the day, what they were looking for is percentage improvement.
Right.
Now here we've allowed you to calculate the absolute cost, right? We allowed you to put it in, but it's an estimate. But I'm going to show you at the end that you can either present your savings to a customer or an operator either in dollars or percentage, whatever you feel more comfortable with. It depends on your measurements and how comfortable and confident you are with your energy measurements. So yes, COP here is quite poor. So we're going to take care of the RTI. Now these are DX units and they don't support VFDs. So reducing the supply airflow is really limited to shutting them off. And when you shut off DX units, you need to be sensitive to the fact that there may be backflow coming back up through those units. So you may want to put louvers, backflow prevention louvers under that. And you'll no doubt want to connect them together so that if one goes down, the other one comes back up. And you can do that using the icon control. There are controllers now on these crack units allow you to wire them together, network them together so that the failure of one would spark the startup of another. And if you were to go to new DX units, there is some advantage because you can put VFDs on new DX units, but I will point out that they don't go down that low. For a data center like this, you couldn't get rid of the amount of airflow you need to get rid of because they only move down about 20%.
Right.
Is my experience. So, and modeling can allow you to understand, of course, the effect. So the first things we're going to do is improve RTI by shutting units off. Then we're going to improve the air management of the room, and then we're going to walk up the supply air temp to improve the efficiency of the cracks. And if you're using any kind of free cooling at all, it's going to open the window for that tremendously, and your COP will go way up. And it's going to improve the life of your cooling equipment by getting it to run only when it needs to run and run in its design center. So the first thing we did on this particular model is turn units off. So here, if you look, there's only one unit on now, and that's the one over near the load. The load is highest over in this part of the room. So we left this one on, and just to see the effect, just to see what would happen. So if we look at our summary report now, we'll find that the total heat load is still the same, but the flow rate is 15,000 compared to the 10 that we need. So naturally, when we go down and we look at our RTI, it's going to be much better. RTI now is 72%. So it's moved from 18 to 72. We still have no problems with heat. Of course, we're running it at 55 degrees, which is a lot of the reason why. Our COP has improved to 3.36. Now, these were current measurements made by the customer. So all I did in these calculations is, in the first run, I used all of the cracks, used the current supplying them all. And in this one, I used just the current, just the wattage supplying one of them. And guess what? COP moved way up because I turned the fans off and turned the pumps off on the other units. So things got a lot better. Still too cold, but the operating cost dropped to under $100,000 from 140. Still running it at 55, still too cold, and of course, but if we take a look, Liz, now at the same chart, the same plot of flow rates from the tiles, you'll see that it's a lot less of a hurricane. So it's still coming, it's still leaking back.
Still
but
excess, but not as bad.
Not as bad, right? And if we
you can see, you can zoom in on some of those, like at the end there. You can zoom in and just show that, in fact, show how the flow does go just directly from the tiles into the rack. So the ones on the lower left, it's a nice illustration. If you zoom in on just turn it a little bit, you can just see how.
Yes. Yeah. This is how it's supposed to work right here. This is what she's talking about.
Yeah, a couple of those places.
The air is supposed to come up out of the tile and go right into the rack.
Right
so here's an example of it behaving properly.
And at the very end of the room, you can see it as well.
Yeah, it's right down here. Yep.
Yeah.
That's how it's supposed to work. So if you look at your cut planes here now at 6 feet, a lot of people like to stare at these. This is another representation. You can see here that it's in much better shape than it was before with respect to temperature. Yep, it's hot in the hot areas. It's cooler out. If we take a look now at the rack inlets, we find that if we look at our chart, we'll see here that we're beginning to come into compliance in certain areas. Look at the full range, you're going to see quite a bit of variation, as you can see. Because we're not managing the airflow, we've got quite a contour over here, quite a bit of temperature over here. So, and down here as well. It's also interesting to note over in this region, you can see the air, high velocity air coming right by here and causing it to be cold down at this end, but hot during this end because we're so close to that high velocity air.
Close to the crack.
Too close to the crack. Very typical. So in the next model, what we do is we use a little bit of cold aisle and a little bit of hot aisle, a little bit of both. But fortunately, in this room, we have a ceiling plenum, and that helps with respect to hot aisle in a few key areas. For example, here's a set of equipment over here up against the wall, and it's got ceiling plenum, return grills up above. Very nice place to put some curtains. Another natural hot aisle in this room, that's a hot aisle. Another natural hot aisle is right here. To get that distribution of temperature a little more even that we were just looking at, we can box in this region right here, and you see I've started to do that with these baffles. And also I've blocked in between the servers here. These are typically in the room what you put is curtains. Here what we're using is simple baffles to do this. Now down here at this end of the room, I did a little bit of work with cold aisle containment. Here we boxed in the racks, put a curtain across the top, across the end. This is a cold aisle, and I'm trying to preserve the coolness down there. And also in these corners I put a sheet across and put a little edge here on this side of the room. You'll see from an energy point of view, nothing changed because we didn't change anything with respect to this area right here. I mean, the curtains don't do anything in this region. But what we were able to do with respect to temperature is things are a little more uniform now. You see how the racks are a little more uniform than they were. So we're doing a better job managing air than we were earlier. And that helps as we begin to raise temp. So once we've got the curtains in place and done a little management, now we can begin to drive up supply temp. So here we're driving supply temp up to 65 degrees. And let's see how we do with respect to conformance. And you see it's all green. So we're doing much better. Now we've got the racks in compliance. They're all in compliance. We're operating the set point at 65 degrees of supply air. We've got one crack unit on. Now many of you will say, and look at the COP now at 4. Now the way I got that was to take the COP from the earlier run and just multiply it by the ratio of the temperature. In this case, I moved up 10 degrees of supply air temp, which gives me 19-20% improvement in COP. So I just multiplied 1.2 times my old COP to get the new one. So you can either use measured values on the input or you can use the COP value itself. You'll want to use them at different times. Originally I was using the measured values, but projecting forward, if I move up the temperature in the room, I used the COP value itself, driving the cost down to $84,000. Now I currently, Liz, don't have this set up as an N+1 room. I've only got one crack sitting there on. But what that icon control allows you to do is to network the two units together so that if a crack goes down, the other one will come up. And what you can do...
But there again, yeah, it's a good idea to do the simulation, with one, if you know that that's the way you're going to run, to do the simulation with each one of them on, individually.
That's exactly
all alone, just to make sure that the flow that the flow patterns can handle it.
Yes.
Flow in the room is adequate for it.
Exactly correct. So what you would want to do here, right now I've got this particular crack unit turned on, AC1_3. I'd want to switch them, rotate them around, try this same model with each of the others turned on individually to make sure that it conforms to the specification. If so, you could set the icon unit up so that any one of the other three would come on, and you'd still have your N+1 case. So this one works pretty well. This is the optimal case. You'll see here now that if we go back and we take a look at pathline plots again, things are even better behaved than they were. We've got the cold contained here, so it can't leak out of there. I've got good containment down that end of the room. I've got hot aisle containment up here. I can show you the hot being trapped. These get a little busy with a ceiling plenum return, but as you zoom in, you can see the hot coming straight up out. The hot temperature, if we take a look at the return temperature in our summary report, is in pretty good shape. Let's take a look at our return temps here, and we see, yeah, we've got a 15-degree delta across. That's pretty good. We'd love to see 20, but 15 is not bad. We'll take it. And so that's our best case. Now, you can take these summary reports that I was just showing you and drag them into Excel because we support integration of all of our output with Microsoft Office. I'm showing you this in PowerPoint. You can also create Excel spreadsheets by dragging the summary reports into Excel. I did that for each one of them and then put the cases side by side on that energy chart. So here's our summary. We went from 1.59, or PUE of over 2, down to 1.37. We went from a cost estimate of 147 to 84. That's a $58,000 delta. And as I said earlier, users may not feel comfortable predicting the actual cost of operation. They may want to use percentages and say, Mr. Customer or Mr. Operator, I think I can save you 40% by doing these changes. So on a budget of $150,000, 40%, you can do your own ROI. It happens quick. And all we did here was switch things off. Now, we probably also put backflow preventers in place, but that's just sheet metal, louvers, not complicated, not expensive. And also here we put some curtains in place, which aren't expensive either. So that's a quick overview in the time we have. We're just about up on 4 o'clock. So let me just summarize. We defined a few key parameters. We defined COP of the room, which is very highly correlated to PUE. We defined RTI and RCI as two other metrics that we use to measure efficiencies in the room. We then optimized these parameters in a process that used CFD to make sure that whatever decision we were making would work and still keep our racks within specifications. And you do need to make some trade-offs between RTI, supply air flow, and supply air temp to make sure that they are balanced. And you can do this all in CoolSim, making it really quite easy to optimize. So with that, Jen, I'm going to turn it back over to you, and you can go ahead and open it up and begin to take questions from our audience.
Excellent. Yep, and we do have one. The first question is, what is the optimum inlet temperature into a server rack, and what is the optimum temperature on the outlet side of a server rack to ensure best server rack performance from different server manufacturers?
Well, yeah, it depends, as it turns out. The inlet temperature that we see people leaning towards the most, and Liz, tell me if you feel anything differently here, is about 80 degrees. I mean, the specifications for inlet temp have been rising, and the new specifications that have just been put in place by ASHRAE are, in fact, quite high, above 90. But most customers are happy with 80.6, 80.6 on the inlet. You want a delta T of 20 degrees would be great. I've seen a lot of them go as high as 30 degrees, which is going to put your outlet temperatures at 100, 110. So that's kind of where we're seeing. Is that your perception as well, Liz?
Yeah, I mean, I think 80.6 is the upper limit of what ASHRAE recommends. So, and I think most people don't feel comfortable having all their servers having that as an inlet temperature. I think they kind of aim to have something a little bit lower. But the goal, I see people trying more and more to raise the rack supply temperature to, 70 or 75 degrees in hopes that they can keep it between 70 and 75 degrees for the bulk of the equipment in the room. The problem is that mixing occurs. So some of the exhaust air, which is quite a bit hotter, as you noted, especially with the newer equipment, some of the exhaust air mixes with the supply air, heating it up. And so, you've always got that to be worried about. That's why it's important to know where the air is flowing. Not how much of it is there, how much, not just the amount of airflow, but where is the air going?
Right.
And, what's it doing?
Okay. Yep, we have another one. How are racks modeled? Is the power distributed uniformly?
In this model, I did use uniform distribution of power in a rack. And the reason is that it is a colo provider, and they have no idea what's going to be in those racks anyway, so that's the best they could do. CoolSim does allow you to model more granular than that. In our 3.2 version, we allow you to put equipment into the racks and model heat loads down to 1U level and put the loads anywhere you want in the vertical direction. So in this particular model, I did it at the level of average watts per rack, which is uniform, but it doesn't have to be that way, is I guess the point.
But that's appropriate if the gaps are blanked. In other words, if any slots that aren't filled with equipment are blanked. I mean, I think that's a very appropriate approach to
Right.
take.
Yes, it is. At least my experience, it is.
Mm-hmm.
Okay.
That is all I have for questions right now.
All right. I'd like to thank the audience for attending, and please provide us feedback about this webinar. If you'd like to see something modeled that you are interested in, or you have a data center that you're interested in having us take a look at, we're willing to consider it for sure. In future broadcasts, it's always more fun for us to have real live data centers to model than, of course, making them up on our own. So we'd be willing to do that. And on behalf of Liz and Jen, myself, thanks everyone for coming, and we'll be doing another one in the next month or two. Don't know exactly when yet, but we'll definitely put a newsletter out to you and let you know. Jen, any last words?
That's it. Thanks, everyone. Look forward to having you attend a future webinar, and look forward to hearing from you if you have an airflow or thermal management need. Thank you.